The sun has been very active lately, and it's about to undergo a critical and fascinating change: the reversal of its magnetic field. This phenomenon occurs roughly every 11 years, marking the midpoint of the solar cycle, and it has far-reaching implications for us here on Earth. In fact, it's possible that any day now, the sun could pose a serious risk that could result in complete chaos and disaster for everyone on the planet. As you're about to discover, the sun's magnetic field is generated by the movement of electrically charged gases in its interior, a process known as the solar dynamo. Over time, this magnetic field becomes increasingly complex and twisted due to the sun's rotation and convective motions. Eventually, this process leads to a complete reversal of the magnetic polarity. The north magnetic pole becomes the south magnetic pole and vice versa. So let's break down the whole process and get a closer look at the sun. The sun is composed primarily of hydrogen and helium in the form of plasma, a state of matter where electrons are not bound to atoms, resulting in a mixture of free electrons and ions. The sun's interior is divided into several layers, with the core at the center, surrounded by the radiative zone and the convective zone. The core is the sun's innermost region, where nuclear fusion occurs, converting hydrogen into helium and releasing vast amounts of energy. Above the core lies the radiative zone, where energy is transported outward through radiation. In this region, energy moves slowly outward as photons are repeatedly absorbed and re-emitted by the solar plasma. The outermost layer of the sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises towards the surface, cools, and then sinks back down, creating convective currents. The solar dynamo mechanism operates primarily in the convective zone and the tachocline, a thin layer that lies between the radiative zone and the convective zone. The tachocline is crucial because it's where the sun's differential rotation and shear flows play a significant role in generating the magnetic field. Now here's something interesting that you might not have known. The sun does not rotate as a solid body. Instead, different parts of the sun rotate at different rates, with the equator rotating faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the magnetic field lines, amplifying the magnetic field. The solar cycle is an approximately 11-year cycle during which the sun's magnetic field goes through a series of changes, culminating in a reversal of its polarity. This cycle is driven by the solar dynamo and involves several stages. At the beginning of the solar cycle, the sun is in a state of solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is relatively simple and bipolar, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the emergence of magnetic flux from the sun's interior. These sunspots appear in pairs with opposite magnetic polarity and migrate towards the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes highly complex and tangled due to the continuous twisting and shearing by differential rotation and convection. As solar maximum wanes, the magnetic field begins to reorganize itself. The twisted and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity. The north magnetic pole becomes the south magnetic pole and vice versa. This process is facilitated by the migration and cancellation of opposite magnetic flux regions. After the polarity reversal, the sun enters a period of declining activity, leading back to solar minimum. The magnetic field simplifies again, and the cycle is ready to start anew. Currently, we're in the solar maximum stage, and the sun's magnetic field is going to flip. During this stage, we can expect to see some incredible activity from the sun that could be as deadly as it is fascinating. However, the sun's magnetic field reversal is not a sudden flip, but rather a gradual process. As the solar cycle progresses, the sun's magnetic field undergoes a series of changes. When the magnetic field is at its most twisted and tangled state, it reaches a tipping point and begins to reorganize itself, resulting in a flip. So, do we know when the sun's magnetic field is about to reverse? Scientists monitor the sun's magnetic activity using a variety of tools and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's magnetic field and track changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots during solar maximum. Sunspots appear more frequently and are more pronounced. As these sunspots migrate towards the sun's equator, they signal that the magnetic field is becoming more unstable and is preparing to flip. While we're on the topic, let's dive a little deeper into sunspots. Sunspots form when the sun's magnetic field lines become twisted and tangled due to differential rotation. Since the sun is a giant ball of gas and plasma, the equator of the sun rotates faster than its poles, causing the magnetic lines to stretch and warp. When these lines loop above the sun's surface, they inhibit the convective flow of hot plasma from the sun's interior. This results in the cooler, darker patches that you see in sunspot images. They kind of look like big holes in the sun. Sunspots are not just fascinating solar features. They can sometimes produce very powerful solar flares and coronal mass ejections, CMEs. These phenomena release vast amounts of energy and charged particles into space. When directed towards Earth, they can interfere with satellite communications, disrupt power grids, and pose risks to astronauts in space. Additionally, the increased solar activity can enhance the auroras but also increase the radiation levels in Earth's upper atmosphere. So while we're on the subject, let's dive a little deeper into the difference between solar flares and coronal mass ejections. While solar flares and CMEs are both powerful bursts of energy from the sun, it's important to understand that they differ significantly. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit a lot of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as a flash of bright light and heat on the sun's surface, similar to a huge explosion. On the other hand, CMEs are massive ejections of solar wind and magnetic fields from the solar corona. Think of them as giant bubbles of gas and magnetic fields that get hurled into space. When a coronal mass ejection occurs, it sends billions of tons of solar particles into space at very high speeds. That said, you can see that solar flares and CMEs are related, but they're not the same. A solar flare can happen independently, but sometimes a particularly powerful solar flare can be accompanied by a CME. So, while a solar flare doesn't always cause a CME, they can be linked. When it comes to danger, it depends on what we're talking about. Solar flares can disrupt radio communications, navigation signals, and pose a serious risk to astronauts in space due to the intense radiation. CMEs, however, can have a more widespread effect. They can cause geomagnetic storms that disrupt power grids, satellite operations, and those beautiful auroras. They can also increase the radiation in Earth's atmosphere. While solar flares are intense and potentially harmful, CMEs tend to be more dangerous on a broader scale because of their ability to affect Earth's magnetic field and, in turn, become a serious threat to Earth's technology and infrastructure. Something else to consider is that during periods of high solar activity, the amount of cosmic radiation reaching Earth also increases. Satellites and other spacecraft are particularly vulnerable to increased solar activity. The charged particles from the sun can cause damage to electronic components, interfere with communication signals, and even alter satellite orbits. But aside from causing damage to technology and infrastructure, what else can happen to the planet? While the sun's magnetic field reversal does not directly affect Earth's climate, the associated changes in solar activity can have an impact. Some studies suggest that variations in solar radiation can influence weather patterns and climate dynamics. For example, increased solar activity can lead to a slight warming of Earth's atmosphere, which could worsen existing climate change trends. It could be said that auroras are probably the only positive thing we experience here on Earth. One of the most spectacular effects of increased solar activity is the intensification of these ghostly lights. These natural light displays, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and the atmosphere. We hear a lot about the northern lights, but these lights can also be seen in places around the South Pole as well. During periods of high solar activity, auroras become more frequent and can be seen at lower latitudes, providing breathtaking night sky shows. But aside from the beautiful auroras, there are more negative things about the sun's magnetic reversal that could occur. And if we're not prepared, something might happen resulting in chaos around the globe. One of the most significant risks associated with a magnetic field reversal is the increased likelihood of geomagnetic storms. These storms occur when solar wind, filled with charged particles, interacts with Earth's magnetic field. In extreme cases, they can cause widespread blackouts and damage to infrastructure. One such event has happened before. On the morning of September 1, 1859, astronomer Richard Carrington was observing the sun through his telescope as he had done countless times before. However, what he witnessed on this particular day would go down in history as the most significant solar storm ever recorded. At 11:18 a.m., Carrington observed a brilliant flash of white light emanating from a cluster of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever documented. The white light Carrington observed was a huge solar flare, an intense burst of radiation resulting from the release of magnetic energy stored in the sun's atmosphere. This flare was so powerful that it unleashed a massive coronal mass ejection, CME, directly towards Earth, traveling at an astonishing speed of over 4 million miles per hour. The CME reached Earth in just 17.6 hours, a remarkably short time considering the sun is 93 million miles away from us. When the CME collided with Earth's magnetosphere, it triggered a geomagnetic storm of unprecedented intensity. The impact was immediate and far-reaching, disrupting the planet's magnetic field and inducing currents in the ground and in telegraph lines. Telegraph systems, which were the backbone of global communication at the time, experienced severe malfunctions. Sparks flew from telegraph machines, operators received electric shocks, and some telegraph stations even caught fire. In some cases, the induced currents were so strong that telegraph operators were able to send and receive messages with their telegraph keys even after disconnecting the batteries. One of the most striking and memorable results of the Carrington event was the spectacular display of auroras. During the Carrington event, the auroras were so bright and widespread that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the skies light up with vivid colors. The auroras were so intense that they illuminated the night sky to the point where people in the northeastern United States could read newspapers by their light. In the Rocky Mountains, gold miners were reportedly woken up by their brightness and, thinking it was morning, began preparing breakfast. People described the sky as having glowing red, green, and purple curtains of light dancing and shimmering across the horizon. Now, just imagine if a solar storm of the magnitude of the Carrington event were to hit Earth today. The consequences would be nothing short of catastrophic. The sun is undergoing a critical change, the reversal of its magnetic field, a process that occurs approximately every 11 years as part of the solar cycle. This event, driven by the solar dynamo, can have far-reaching implications on Earth, potentially causing chaos and disaster. The sun's magnetic field is generated by the movement of electrically charged gases in its interior, resulting in a complex magnetic field that eventually reverses its polarity. The sun is primarily composed of hydrogen and helium plasma, with energy produced by nuclear fusion in the core. This energy is transferred outward through the radiative zone and then by convection in the outer layers. The solar dynamo mechanism, which operates in the convective zone and the tachocline, generates the sun's magnetic field. Differential rotation of the sun, where the equator rotates faster than the poles, stretches and amplifies magnetic field lines, driving the solar cycle. Currently, the sun is in the solar maximum stage, where sunspots and solar activity are at their peak, leading to potential risks such as solar flares and coronal mass ejections, CMEs, that can disrupt satellite communications, power grids, and pose risks to astronauts. Scientists monitor the sun's magnetic activity and sunspot behavior to predict the timing of the magnetic field reversal. Sunspots, which result from twisted magnetic lines, can produce solar flares and CMEs, both powerful bursts of energy that impact Earth in different ways. While solar flares emit radiation, CMEs eject massive amounts of solar particles into space. These phenomena can enhance auroras but also pose serious threats to Earth's technology and infrastructure.